Statistics play a critical role in helping SQL Server's optimizer determine not only how many rows will be returned at any given point in the execution plan, but also in figuring out the most appropriate operators given the scale of the plan it's putting together. In this example, we'll take a look at a query and then two different execution plans for that same query, a plan A and a plan B. And just like the optometrist's office, we'll ask you which one you like better, plan A or plan B. True story. I once went to the optometrist and I said, I like B better than A. And he said, I haven't switched anything yet. So here's our query. Take a good look at it. And now, here's plan A. And here is plan B. Which do you prefer? Plan A or plan B? Plan A or plan B? Okay, I'll stop. The correct answer is it depends on the statistics. It may seem counterintuitive to say that an index seek is not as good as a clustered index scan. But in this case, it could be that the number of rows that we need to churn through makes an index seek plus a key lookup a really inefficient route, and it's better to just shovel through with a clustered index scan. So let's take a look at these two plans individually and look at the estimates that come from statistics and see if these really are the best routes given the number of rows we'll get back. Plan A is the plan involving the clustered index scan and parallelism. For this particular plan, we want to pass in the parameter of P1 equals 0. When we run this query and get the execution plan, we see that the actual number of rows and the estimated number of rows are very close together. Relatively speaking, there's very little difference between the two. So in this case, the optimizer has chosen the best possible plan given what indexes are available. That query took 8,187 milliseconds of CPU time. Looking then at plan B, the smaller index seek plus key lookup plan, we pass in a value of 238 for the P1 parameter. When we run this plan, we get an actual number of rows of 46 and an estimated number of rows of 1. Normally when you look at a plan, you might think that 46 times the number of estimated rows actually coming back would be a catastrophic failure, but to the optimizer, the difference between 1 and 46 is nothing. And that bears out performance-wise too. This query ran in 60 milliseconds of CPU time. So having seen those two plans, we see that the index with the lookup takes about 60 milliseconds. The other one takes 8.1 full seconds. But what happens when the optimizer guesses wrong or gets bad estimates from its statistics? It may end up choosing plan B when plan A would be more appropriate. When that actually happens, the results can be disastrous. Let's see what that means in a quantifiable term. Plan A is the clustered index scan with parallelism. Now we gave it the 238 parameter. When we run this, the actual number of rows is 46 as we expect. The estimated number of rows is 520. It's different this time. This query ran in 1861 milliseconds. Significantly faster, 30 times faster in fact, than the previous run where it got to use the index seek plan. Let's take a look now at plan B with parameter A. So this time we're passing in 0 to P1. When we run this, okay, it's a bad sign already because we can see that the arrows that lead from one operator to the next are much thicker than they were last time around. When we hover over, the bad news gets even worse. The actual number of rows, of course, we know is 10.7 million. The estimated number of rows is 1. Because this plan uses things like nested loops and key lookups, small-scale operators that are meant for just a handful of rows, this plan results in disaster. The CPU time that it takes to get through this, looping through 10 million plus rows, is 18,562 milliseconds. Unfortunately, when the optimizer overbids like this, Bob Barker's not there to tell it, you've overbid, let's start the bidding over again. Whether the optimizer guesses an estimate of a low number of values and has a high number of actual rows returned, or the other way around, a high estimate with a low actual number of rows returned, either one can be disastrous for a query. The worst episodes that I've seen of a gap between estimated and actual number of rows have come when the estimate is tiny and the actual number of rows involved is huge. These small-scale operators just don't keep up. They have a ton of work to do, and it's massively inefficient. When this happens, it's a phenomenon known as parameter sniffing. Now, there are some that will argue that parameter sniffing is a good thing because it reflects query plan reuse, which is something we want, sure. But whenever I hear people talk about parameter sniffing, they're usually saying things like, well, I'm so glad we found the problem. It's parameter sniffing. Now we know how to fix it. I don't hear people singing the praises of parameter sniffing. Anyway, keep that little factoid filed away for a little bit later. We'll cover parameter sniffing in a subsequent chapter. Now it's time to turn our attention to where the numbers that we saw as the estimated number of rows in our execution plans came from. We're going to take a deeper dive now into statistics.